So imagine for a second that you're a contestant on this incredibly high-stakes game show.
Okay, I'm picturing it.
Right. The lights are blinding, the studio audience is completely dead silent, and the host looks at you and asks this ridiculously complex, multi-step calculus question.
Oh, that sounds like a nightmare.
Right. But here is the real catch. You are not allowed to pause to think.
Wait, really?
Yeah, you can't work it out on scratch paper. You have to immediately open your mouth and just start speaking the final answer in this single, continuous stream of words. Pure reflex.
I mean, the human brain just simply doesn't work that way. The pressure alone, plus the lack of a working memory buffer, would just guarantee failure, even if you were, like, a world-class mathematician.
Exactly. Yet for a very long time, that is precisely how we have treated artificial intelligence.
Yeah, we really have.
We feed an AI a prompt, and we just expect it to generate this perfect, flawless answer in a single forward pass, predicting one word after another without a single moment of reflection.
Which is pretty wild when you think about it.
It is. So welcome to today's deep dive. Our mission today is to unpack this foundational state-of-the-art research paper that is basically changing all of that.
Yeah, this is a big one.
It really is. The paper is titled ThinkBooster, a unified framework for seamless test time scaling of LLM reasoning. And the core topic here is test time compute scaling, or TTC for short.
Right, and what's so fascinating here is how TTC has become this incredibly powerful paradigm. Yeah, so if we go back to your game show analogy, TTC scaling is essentially the equivalent of finally giving that stressed out contestant a whiteboard, a calculator, and like 10 minutes in a quiet room.
Oh, nice. So they can actually work through different paths.
Exactly. They can scratch out their mistakes, verify their logic, before they ever even touch the buzzer.
That makes so much sense.
By allowing models to generate these longer reasoning chains, or by having them sample a bunch of different solutions, like chain of thought models, can now solve complex math and coding problems that standard single-pass models just completely fail at.
Wow.
It's a total game changer.
Okay, so the performance gains are obviously undeniable here. But that brings up an immediate question for me.
What's that?
Well, if test time compute is really this powerful, why isn't like every developer on the planet using it flawlessly right now?
That is the million-dollar question.
Because when I open up a standard AI tool today, I'm still mostly getting that single pass, blurting out the first thought kind of answer.
Yeah, and the paper actually diagnosed this exact issue. The researchers who are from MBND UAI, ETH, Zurich, and a few other labs, they point out that the current research landscape for test time compute is just incredibly chaotic.
Chaotic how?
Well, it's highly fragmented. You've got different research labs using these wildly inconsistent experimental protocols.
Oh, I see.
Yeah, so like one team might test on models that have native unstructured thinking modes, meaning the model kind of talks to itself in a hidden text block before it answers.
Okay, got it.
But then another team is over there using structured step-by-step prompting. And they all have different compute budgets, so it's just really messy.
Yeah. So they're all basically running different races with completely different rules.
Exactly. And the paper highlights a really glaring blind spot in all these disparate studies. Most of these studies focus purely on accuracy gains. They just want to prove their method is smarter, and they completely ignore the massive computational costs and the latency involved in making an AI think longer.
Okay, wait. I have to push back on that a little bit.
Sure, go ahead.
If I'm a developer building a tool, let's say a really advanced calculus tutor for students, shouldn't I only care if the AI gets the right answer?
I mean, accuracy is definitely important.
Right, because a wrong answer ruins my product. So why does the specific testing protocol or the compute cost really matter to me?
Well, because in real-world deployment, the performance to compute trade-off is absolutely everything.
Oh, because of the server costs.
Exactly. Current released code for these advanced reasoning strategies often just serves as a proof of concept. It severely lacks efficiency. If your super accurate calculus tutor costs a fortune in TFLOPs, which is basically trillions of floating point operations per second, a measure of raw compute, just to run a single query, it's useless for practical applications.
Because you'd go bankrupt running the servers.
Precisely. You can't scale it.
Okay, that makes sense. So to solve all this chaos and the cost issues, these researchers built ThinkBooster.
Yes, the unified solution.
Right. And from what I understand, ThinkBooster is built on 3 main pillars.
That's right.
First, it's a modular Python library with 9 state-of-the-art scaling algorithms and 4 different scorer families.
Yep, lots of options out of the box.
Second, it's a benchmark that finally measures both accuracy and compute efficiency at the same time. like tracking both tokens and TFLOPs.
Which forces everyone to finally show the receipt for how much energy they used.
Exactly. But the third pillar, here's where it gets really interesting to me.
The proxy service.
Yes, it's an OpenAI-compatible proxy service. If you are a developer, you don't actually need to rewrite your application's code to use this.
Nope, not at all.
You literally just change the base URL in your API call to point to the ThinkBooster endpoint. And it acts as this transparent proxy.
It's kind of like magic.
It really is. It automatically applies TTC scaling in the background. It effectively equips your standard underlying LLM with a pro reasoning mode.
And if we connect this to the bigger picture, this completely lowers the barrier to entry for the entire industry.
Oh, so?
Well, it allows everyday practitioners, people who are just building AI agents or enterprise copilots, to seamlessly deploy advanced reasoning.
Oh, I see.
Yeah, they don't have to be AI architecture experts who know how to manage massive parallel memory states. They just use the proxy.
That's incredible. So it really democratizes the thinking phase of AI.
It does. But to really understand how that pro mode works, we have to look under the hood at how the AI actually evaluates itself.
Right, because how does it decide which reasoning path is actually the best one?
Well, the paper breaks it down into two main parts, strategies and scores.
Okay, let's decode that terminology for a second.
Sure. So the strategy is the high-level algorithm. It's the map.
Like deciding the overall plan of attack.
Exactly. It could be a basic best-of-n strategy where it just generates a bunch of answers and picks one. Or more complex ones like beam search or tree of thought.
Right.
And then there are dynamic methods like MUR, which stands for Momentum Uncertainty Guided Reasoning.
Okay, so that's the strategy. What about the scorer?
The score is literally how the AI grades the individual steps along that map.
Okay, and the paper talks about two main ways to score, right?
Yes.
So the first one is using a process reward model, or a PRM. And to me, this is like hiring a really expensive, highly trained consultant to stand over your shoulder and review every single step of your math homework.
That is a perfect analogy. A PRM is a completely separate model trained specifically to critique other models.
Right, but it's super expensive.
Unbelievably expensive. It burns a ton of compute.
So on the flip side, you have the uncertainty-based scorers, things like entropy or perplexity.
It's a statistical approach.
Right, which I picture as the AI kind of checking its own pulse to see if it's sweating or feeling nervous about a specific step.
Yeah, exactly. It's checking its own internal statistical confidence. If it has 10 options and they all seem equally likely, it's sweating. The uncertainty is high.
But if it's 99% sure, the uncertainty is low.
Right. And what's cool is the paper points out a really crucial technical detail here about white box versus black box methods.
Oh, right, because that determines what you can actually use in the real world.
Exactly. White box methods require access to the model's internal logits, like its raw token probabilities or hidden states.
Which you need if you want to calculate that uncertainty pool.
Yes. But black box methods only need the final generated text.
And this matters because if you're using a closed API, like from a major commercial provider, you can't use white box methods at all.
Exactly. You don't get the logits from a closed API, so you are stuck with black box strategies or hosting your own expensive PRM.
Okay, so that sets up the big benchmark showdown the paper did.
Oh yeah, this is where it gets really fun.
They didn't just build this framework, they really put it through the ringer. They tested it across major data sets like Math 500, Human Evil Plus for coding, and GPQA Diamond.
Yep. And they used a bunch of different models, too.
Right, like Qwen 2.5 Math 7b, Qwen 3.8b, and this massive model called GPT-OSS 120b.
Right. And the results for the math problems were pretty much what you'd expect.
The expensive consultant won.
Yeah. For math, the PRMs paired with beam search hit the absolute highest performance. They crushed it.
But at a massive compute cost, presumably.
Oh, a massive cost. But if you just need raw accuracy in math, they're the gold standard.
But here's the big reveal. When it came to the coding tasks on Human Evil Plus Cambridgeshire, the results totally flipped.
They really did. It was surprising.
Wait, why would the expensive consultant, the PRM, suddenly fail when asked to write Python code?
Well, it comes down to what they are taught. PRMs are predominantly trained on mathematical data.
Oh, I see.
So they completely overfit to the structure of math. Math has a very rigid step-by-step logic. But coding is an out-of-distribution task for them. A PRM looking at a loop or edge cases in code just kind of falls apart.
The specialist is out of their depth.
Hmm.
So what won for coding?
The dynamic strategy MUR paired with those simple domain-agnostic uncertainty scores substantially beat the baselines.
Wow. The pulse-checking method won.
Exactly. Because statistical uncertainty isn't tied to a specific subject like math. It's just a raw measure of the model's confidence.
That's amazing.
And the best part, calculating that uncertainty has basically near zero computational overhead compared to running a heavy PRM.
Because it's just harvesting the math the model is already doing.
You nailed it. It's so efficient.
So moving from these abstract benchmarks to real-world applications, the paper gave a really cool example of optimizing CODA kernels.
Oh, yeah, that was a great test case.
For those who don't know, generating CODA kernel code is highly complex GPU programming. One syntax error and the whole thing crashes.
It is notoriously difficult.
But they use that massive GPT-OSS 120B model with ThinkBooster's offline best-of-end strategy and a PRM. And what was the result?
A 5% drop in syntax errors and a 4 percentage point increase in overall correctness over the baseline model.
Which is huge for developers. It saves so much time debugging.
It really does. And speaking of debugging, ThinkBooster has one final feature that is just incredibly cool.
The visual debugger.
Yes. When an AI is doing all this complex reasoning, generating candidates, and pruning paths, it's usually just this invisible black box to the user.
Right, you just get the final text.
But the visual debugger gives you an interactive web interface. It allows developers to visually inspect the entire reasoning trajectory tree.
Oh, wow. So you can see the exact branches it explored.
Exactly. It shows you exactly why the AI pruned one candidate answer and why it escalated another one. It even gives you per candidate score breakdowns.
That is invaluable. You aren't just getting a better answer. You can actually look under the hood and trace the AI's logic step by step.
It turns debugging from a guessing game into a literal science.
So stepping back, ThinkBooster really bridges that gap between messy lab research and practical deployment.
It absolutely does.
It proves that giving models a structured way to think and self-evaluate, like using that uncertainty score for coding, is incredibly powerful.
And efficient.
Right. So what does this all mean for you listening today? Whether you're building tools or just using them, accuracy isn't just about the base model you use anymore.
No, it's not.
It's about the compute you allow it to have at inference time, the time you let it think.
But this raises a really important caveat that we have to mention.
Let's hear it.
The researchers used theoretical TFLOPs in the paper to get these clean, hardware-independent comparisons.
Right, which makes sense for a study.
Sure, but the next frontier in the real world is going to be measuring actual wall clock latency, the literal time you are sitting there waiting for an answer.
Because theoretical math doesn't always equal real-world waiting times.
Exactly. Wall clock latency relies heavily on server optimizations, things like VLLM prefix caching.
Prefix hashing.
Yeah, so when the AI generates multiple reasoning paths from the same prompt, prefix caching stores the original prompt in the server's RAM.
Oh, so it doesn't have to compute the whole prompt over again for every branch.
Exactly. It saves massive amounts of time. So a method that looks expensive in TFLOPs might actually run surprisingly fast if the server is optimized well.
That makes total sense. Hardware optimization is really the next big hurdle.
It definitely is.
Well, to wrap things up, I want to leave you with a final thought to mull over. We started by talking about that stressed-out game show contestant, forced to rely on pure reflex.
Right.
And for years, the AI industry's primary solution to make that contestant smarter was just to build a bigger brain, training massive trillion-parameter models at astronomical financial and environmental costs.
Which is just not sustainable.
Exactly. But if AI can now dynamically adjust its own thinking time based purely on how uncertain it feels about a specific step, if it basically knows exactly when to check its own pulse, will the future of AI development shift?
It's a huge question.
Will the industry start building these massive static brains and instead focus on teaching much smaller, highly efficient models exactly when to stop, reflect, and pull out a virtual whiteboard to double-check their work?
It certainly looks like we're heading in that direction.
It might just be that the true secret to intelligence isn't knowing everything instantly, but knowing when to take a breath and think.